Thank you very much for joining another edition of our Liftoff webinar series presented by Lyft. My name is Joe Steele. I'm the Senior Director of Communications and Legislative Affairs here with Lyft. Hope everyone is doing well and staying safe as we continue to work remotely in various places in or around around our places of business or even from home. Today, we are proud to welcome PDA, Jiten Shah, and PDA Product Development Analysis to talk to us a little bit about their work in lightweighting and reverse engineering when it comes to supporting the Department of Defense. PDA has been a longtime member of Lyft, and we are happy to have them present to us today. A few housekeeping items I'd like to remind you of. If you can, remember to keep your phones and computers on mute. That would be great. We want to eliminate as much background noise as possible. We are recording this webinar as we do our Liftoff webinar series and post them on our website. So you can visit them later, or you can share them with folks who may be interested or folks who were unable to join for one reason or another. I do want to share a few things about Lyft before we get started with Jiten and PDA for those who may not know who we are and what we do. Lyft is one of 16 National Manufacturing Innovation Institutes, collectively known as Manufacturing USA. We are based in Detroit, and our goal is driving American manufacturing into the future through technology and talent development. That is really what we are calling smarter manufacturing. We believe that smarter manufacturing is the key to our national economy and national security because we know how large the manufacturing sector is in this country. And so as we go forward, the next industrial economic powerhouse will be the area or region that kind of conquers smarter manufacturing first. And we want that to be the United States of America. So how do we think about smarter manufacturing? We think of it as the manufacturing equation, which is the connection of materials, processes, systems, and talent. We look at the whole manufacturing equation holistically to make sure that we're solving problems and not just solving them piecemeal, which could lead to challenges down the road. Not just materials, not just processes, but the whole holistic system. So we have two programs at Lyft in which we're tackling this. The first is our technology program called Leading Innovations for Tomorrow. And the second is our talent program, which is Learning Innovations for Tomorrow. We will get into both of those in just a second here. Leading Innovations for Tomorrow is the technology program, as I mentioned, where we are doing the work of connecting materials, processes, and systems via these four pillars that you see on the screen here. This is where most of our work resides, from digital analysis and computation to actually doing the work and joining and developing products and implementing them into the systems. You can take a look here. This is a little bit deeper look into the technology program and all of the various work that resides under those four pillars. More information can be found on this on our website, lift.technology. But you see, we kind of run the gamut of work from digital twin to advanced joining and hypersonics work even as well. On the talent side of the equation, Learning Innovations for Tomorrow, we are innovative there as well, creating new tools, pathways, and venues. And it really revolves around our Ignite Mastering Manufacturing curriculum that we developed with funding from the Department of Defense to help expose high school students mostly to the world of advanced manufacturing, because we want to make sure that the pipeline of talent for advanced manufacturing in the future exists and is robust. We know there is a skills gap where 2.4 million jobs over the next 10 years will go unfilled because there are not enough people to take the jobs that are available or will become open over that time. So we want to make sure that we are encouraging folks to look at advanced manufacturing as a career. And we do that in our facility at our Lyft Learning Lab that you see pictured there. Pre-COVID, we had about 120 students any given day coming through our facility to learn about advanced manufacturing or to take part in our world-class certification programs. We are certifying people for jobs of today. We are concerned about the jobs of the future, as I mentioned, but we are certainly working to help folks find the jobs that are available today in welding, CNC, robotics, industrial technology maintenance, which takes us to Operation Next. Operation Next is one of the programs that we are most proud of here at Lyft. It started as a program to help our separating servicemen and women who are leaving the military 6 months before they leave, to give them the opportunity while they're still on active duty to earn certifications in some of the most in-demand advanced manufacturing jobs, welding, CNC, robotics, etc. That has been successful, and we are working towards expanding that across the country. We have funding from the Department of Defense to do just that. It is launched as a pilot, as I mentioned, back in 2018 at Fort Campbell, Kentucky, but it has since expanded to the Michigan National Guard, and their spouses can take advantage of the program, the Florida National Guard and Reserve and their spouses, and we are looking to make some announcements coming up still this year to some more defense facilities where this program will be expanded. It also was expanded actually into industry in response to the COVID-19 pandemic and the CARES Act that was funded by Congress last year and passed by the president, passed by Congress and signed by the president last year. We are piloting, taking it into industry here in Detroit, as well as Pittsburgh, to help displaced workers and small to medium-sized manufacturers get off the mat, if you will, after the pandemic and really regain their footing as the economy recovers. So I mentioned one more thing. We are a membership-based organization, a nonprofit 501c3 based here in Michigan. So what do members, what do they benefit from? Well, they benefit from all of the things listed here. We are a trusted advisor providing the best advice we can to help companies and organizations move towards smarter manufacturing. We're a technology accelerator, as I mentioned, and Jiten will get into a little bit today. Technology showcase. If you have not visited our facility in Detroit, please do so. You can take a tour of the facility on our website as well to see the equipment that we have there and the capabilities. We are a connector and a convener, which is why we're all here today. So thank you very much for joining us once again. Talent developer, I already touched on that, both on the high school community college side as well as the incumbent worker side. And finally, we're a government partner. We look to break down the barriers to allow people to work with the Department of Defense. And I think that Jiten and PDA is a great example of that, and we will hear from them today, hear from him today. So feel free to give us any questions. You can contact us directly on our website or via the email or via the phone number. Be sure to follow us on LinkedIn and Twitter as well to see updates of what we have going on as an institute. So with that, I will turn the program over to Jiten Shah to talk to us about PDA's work and what they have going on. So I will stop sharing, Jiten, and the show is yours.
Great. Can you see it okay?
Yes, we got it. Thank you.
Excellent. Yes. Hello, everyone. Good morning or good afternoon, depending upon where you are. I'm Jiten Shah, founder and president of Product Development and Analysis, PDA LLC. These two topics, lightweighting and legacy parts, I liked what Lift calls them the orphan or the obsolescence. These are the two top priorities of the Department of Defense, mainly for the sustainment and operational efficiency. So we thought this would be, and we have done extensive work in these two areas. So I thought we would share and trigger some interest and some provoking thought process. Quick background, PDA, we have been doing serving metal casting since '93, over 27 years, over 165 OEMs and casters in military transportation. Also, in addition to Lift, we have been a member with contract research projects with America Mix and MXD. And we provide a turnkey solution. So, and we are widely engaged with professional societies like American Foundry Society and Investment Casting Institute. So what we do is we clearly understand the requirements and expectations and come up with a fully integrated solution essentially utilizing the state-of-the-art technologies, could be virtual simulation or ICME or 3D scanning and additive manufacturing. And we have also done quite a bit of conversion for lightweighting objective, converting a lot of fabrications and forgings into casting in different alloys. And I just was adding up, I think we have added over 3,000 tons of castings to the casting industry. And in addition to metal, we also do plastic composite and essentially new product development, reverse engineering, which is what I'll talk about, redesign, and we do get into some failure analysis, which leads us into reverse engineering. I have a couple of case studies on that. In terms of tools, we have obviously a couple of CAD packages, FEA, quite extensive, CFD, and our core competencies on casting process simulation, which I'll dabble a little bit deeper, and then 3D scanning, non-contact. And as I said, we do turnkey, so we do have, do contract manufacturing and provide components. You will see that too in a minute. So this is our overall product process development. It could be for new product as well as for reverse engineering. And one key distinction is when we get into dealing with metal casting, we don't isolate product from processes. We think about the best way to make that particular component the best process and the applicable list of alloys we pick and choose through value engineering. As you can see here in our toolkits, we have extensive knowledge base and developed our own tools and develop few for the professional societies that we use, which really helps us on value engineering. And over the last, I would say 5-6 years, quite intimately involved with additive manufacturing as part of the toolkit. But I go back when I started the company, we used to call it rapid prototyping, and so I've been involved into new product development using either rapid prototyping or additive manufacturing. But one thing, another I would point out that here is we extensively work in a collaborative environment. We are not the manufacturer, so we have partners we work with, and our OEM customers, we all collaborate, go through negotiation, keeping our ultimate goal in mind, which could be either weight reduction, obviously not adding cost in doing so, and pay attention to the timeline and the schedule. So, you start off with a concept, develop initial design, final design, do prototyping, and then get into the production. Typical inputs we get, the key are the customer requirements, goals, expectations. In case of reverse engineering, we get a sample which could be a broken or a brand new, and that becomes our input, and we get into developing the shape, optimizing the shape, and developing the risering and the gating, the whole plumbing system, simulating with process parameters in mind applicable for that particular component. And then after we have meet our targets, then you get into launching and deploying the technical data package, which could be the 3D models, drawings, and a bunch of reports. This is our core competency is on metal casting. That's how I started the company in '93. We have tremendous experience and database for various processes and alloys, as you can see here, anywhere from titanium. We did for Rock Island Arsenal, investment cast for aerospace to a stationary power generation oil pan about 12 feet long, huge component, and some valve bodies for the naval applications or the marine applications. When we talk about when we talk about advanced simulation capabilities, the technology where it stands and comes out very handy, especially when you are dealing with lightweight, thin wall components. There is always a concern with the distortion and building of residual stresses. So we have that capabilities, and we have done series of projects. This is an example of a magnesium housing for aircraft gearbox. So lightweighting essentially is for improving the performance, efficiency, or payload, and has tremendous applications. One I would consider while you are at a new product development stage. The old days we used to design quickly and then come back and optimize. Well, now the trend is do your best right from the get-go and go through design optimization before you launch a new product. So lightweighting related technologies are quite important. And then obviously redesign, reverse engineering for optimizing the performance. And I folded in my conversion scenario under reverse engineering or redesign, kind of a subset. And also the conversion as a separate topic, mainly driven by from the cost reduction point of view and the supply chain issues. We have seen quite a few examples where the long lead time and the supply chain drying up necessitated look for an alternative method, and we have converted quite a few with that. This is one of the flagship project of Lyft. Happened to be part of it, where we took a legacy part by an OEM in service for over a decade or so, and using the new alloy we developed, and with the design optimization, we were able to knock 40% weight out, and went through the whole prototyping and PPAP, low volume production, in order to get the durability testing. We used generative designs, auto topology optimization. I would say very powerful tools, very useful to see which areas you can take the weight out. But the caution is you don't want to straight away use those outputs and try to make the castings, because you will never be able to manufacture those consistently. So there has to be some design for manufacturability related consideration, along with virtual simulation, to validate and come up with more manufacturable solutions. So you can see here, extensive process simulation, where we were able to predict the microstructure, mechanical properties, and wanted to make sure it has the desired soundness. One of the issues you get into when you try to make 2.5 millimeter wall iron castings, you have to be concerned with the carbides or the white cast iron formation, which is going to impact your ductility and the fatigue performance. So I think we came up with a pretty good solution and got good results. The next project I was involved, which is thin wall aluminum casting. These are the first 4 or 5 projects LIFT rolled out in the very first year of their existence, and we were fortunate enough to be a part of it. This was led by Boeing, and this focused on thin wall casting development for aluminum alloy using high pressure die casting and with a super vac. And we took a part which is the side impact beam of an automotive company, about 1.2 meter long and 3 millimeter wall. At some areas, we had almost close to a 1 millimeter wall, and it was a challenge to come up with the process parameters and the gating system to make sure it fills in without any hot tear or porosity in the critical areas. So we were able to successfully simulate, and Boeing went back and validated through extensive X-ray, and they found sound component. Also, another thing we did here is we designed and developed, because we were working on a new alloy, fluidity die that we designed and built working with the Ohio State University team. And that's where we ran some trials and validated and calibrated our simulation by running partial shots in the die cast. One thing we do, and I do talk about, is what I have seen in the metal casting industry is either over specifying the component by saying, hey, I want the entire casting level 1. When you do so, you really pay a price because it makes very difficult to manufacture consistently level 1. What the suppliers end up doing is basically ending up, doing a weld repair if it's a weldable alloy, or if it's not, then you end up, having a high scrap rate, and ultimately OEM they end up paying for it. So what I've been publicly talking about is you should look at the component from the high stress area, the service life, and the fatigue failure mode. And by doing critical flaw calculations, then you back calculate and come up with the casting acceptance criteria. And that's where ICME based modeling simulation come out very valuable. So what you do now is you have a casting with zoning with different levels of severity for different types of defects. Now you are giving something to manufacturers that they can make it cost effectively, consistently. And so I just wanted to dwell a little bit on that. Another exciting time, I would say, and it fits in very well with reverse engineering and legacy part production, is the availability of tooling-less casting processes, essentially, using additive binder jet, where you straight away make the mold and the core, or you make wax-like components, wax-like patterns, and then you do investment casting. So what we have done with this technology is we have literally taken out the tooling related design, fabrication, manufacturing, time and cost out of the equation, and then subsequent headaches of storage and maintenance of the tooling. That's one of the key issues that the DoD and especially DLA is running into, is they have the contracts, acquisition by contract. So supplier A finished the contract and the tooling is owned by the government. That tooling either ends up at the government depot or not well maintained, And when the next order comes, they cannot find the tool, or the tooling has been damaged because nobody really took care of it. So this is part of the issues we have with the legacy part acquisitions in the DoD, especially in the DLA. And I think additive comes out very handy where you essentially take the toolingless approach. Also, it has tremendous fit into especially the DoD, where it's a low volume production environment. And it also brings agility, where you can make changes into the design and go with the digital manufacturing as opposed to the traditional tooling and modifying the tool, and all that time and the cost associated. You really get that out of the way. So another thing we have seen is with the additive, especially 3D printed sand, that these are digitally made, so there is no tooling wear and tear related. So every time you make a mold, it's dimensionally accurate with the precision of maybe 0.5 millimeter. And so I call it precision sand casting, because it really helps you further narrow down your tolerances, make the walls thinner, and get the light weighting. I'm sure most of you are aware of the process, so I'll just zip through. This is making, 2-in-1, I call it, making mold and core out of the same machine without any tooling. And on investment casting, you can see, an example of printed wax pattern looks exact replica of the casting, but you are eliminating the need for wax injection dies. And as the photo indicates, the storage, maintenance, and upgrade, all that logistic is really gone out of the window. One thing you can also gain, since there is no tooling with this digital manufacturing, there is no need for drafting or constraints by drafting. So it gives a lot of freedom with the feature placement. You don't have to worry about, since there is no tooling, of withdrawing the tool out of the mold. And that gives you additional advantage of putting features where you want, and gain lightweighting and optimize the design further. So here is an example of a cast frame assembly on your right, converted into one-piece casting with a 17% weight reduction. And the one on the left, by just simply removing the draft, we were able to get about 15% weight reduction. Also, you can think out of the box, where you look at the current casting, how it is connected with, either bolted, welded, and you can bring those features as long as you can. It doesn't interfere with your assembly, but it gives you an opportunity to do a consolidation of multiple components into one piece casting. Like here, we worked on an engine block for a racing car, where we combined manifold with the block, and came up with a design which can only be done with this approach. The differences are here with the additive. We just have the z-axis orientation. You have to make sure your part or the design is oriented, because you will see otherwise staircasing effect, because this is a layer by layer process, the binder jetting. It's really ideal for legacy parts. This is an example from our America Mix project, our partner Hometown, acknowledging their case study, where we took multiple cores and came up with a one-piece core design. You can imagine now the positional tolerance are going to be right on the money, as opposed to the traditional approach where you may see some sloppiness because of the core print clearance. So definitely this gives you much better dimensional accuracy and reproducibility. Another example, core consolidation for ductile iron. This is another lift project, investment cast, and we work with Lockheed Martin. This is tremendous improvement in the fatigue performance. Traditionally, these are made by permanent mold or high pressure die cast options. And we were able to go with the rapid solidification and get better ductility and strength compared to the conventional sand casting. But again, we use additive in order to do this fast forge 6-month turnaround. And ICME was very important in predicting the properties, residual stress, and mapping, and they map very well to the actual results. Switching gears here, reverse engineering. So when we do reverse engineering, typically we get new or used samples, and we always ask for access to higher order assembly, so we know the interaction of that particular piece with other components. Typically we scan, we have in-house white light scanner, but we have access to I used to have like a CMM portable probe with a laser scanning attachment. I have access to that. We also get 2D, either 2D drawings, the old watermark that we can take and build the 3D model, and then deliverable would be the 2D drawing with the engineering drawings with the tolerances and fits. That's a very important area when you get into reverse engineering, because you don't have access to the design engineer who designed this, and you have to engineer, come up with the tolerances and fits. And of course, we then find out the material quality assessment through FEA or hand calculation. We determine the critical areas and features and develop the requirements. And now you are getting ready to make castings and do the secondary processing. This is an example of collective protection system, Humvee mounted, that I was involved in, reverse engineered all the aluminum casting components. Had to go through extensive design validation, come up with the requirement, and we delivered the data package to the Department of Defense, and they use that for their acquisition and get into the sustainment part of it. Another project comes to mind is converted a steel fabrication into one-piece casting design, and we achieved 30% reduction and tremendous saving in cost with the lead time. And this particular component is actually still being used on the destroyer Aegis. You can see that's the targeting radar antenna dish, and the structure we designed. It's about a 5 cubic feet envelope, pretty big sand aluminum casting. Had gone through extensive FEA and rigging and process simulation. Another one is the transmission housing for AAAV, which became expeditionary fighting vehicle, and we were involved in the development of that. This is more of a new product development, but they had design configuration wasn't manufacturable, so we helped them, and we turned around the whole thing in 7 weeks from the time they gave us the model. I have also converted these 500 and 2,000 pound projectiles, used to be out of steel, into one-piece casting, which turn out better performing with a better fragmentation and a footprint. These are being used in the current theaters, or were used, I should say, in the past. Another example for General Dynamics Defense, for a submarine, took a component, converted. This is my a good example to share where it was for a leading food processing company in their captive power plant, and they had a failure of a pump for the boiler feed water, and we did the failure analysis, and we found out what was wrong, and casually asked them, hey, let us know if you need help replacing these components. And they said, yeah, we'll get back to you. They tried to reach the original manufacturer and supplier in Europe. They were out of business, and the client got into the panic before the winter hits. They really wanted to get the captive power plant up and running. Otherwise, would have really costed them of the order of $10,000 a day. So again, this kind of projects, when you find a solution, the payback and the value proposition is tremendously appreciated. So we reverse engineered the main housing and also the bearing housing, and supplied 6 finished assemblies, and they put it into the service, and we also made modification to the alloy. But very successful project. This is again in service for over 2 decades, almost over 15 years. Done quite a bit of work on investment replacement castings using, this is an old technology, SLA, and take SLA and then make the casting. And then this is the one we did it for a locomotive OEM, a replacement part. They just needed one for a locomotive built in 1950s, and all they had was hand-drawn drawings, and we took that and a sample and converted a 3D model, and used 3D printed sand mold, poured it, and supplied just one piece, as you can see here. So reverse engineering, we have tremendous background in military as well as in transportation. This is a people mover system that I've been involved in serving over 25 years with multiple components, predominantly casting, starting with the brake disc rotor to the whole guiding system to some composite panels. And again, this is a classic where either we get most of the time a used component, and you reverse engineer, taking into account the wear and tear, and develop the dimensions and interface, and do testing validations, because this is for carrying people. So a lot of these are safety critical components, and it's a very low volume. So the big companies are not interested. So this is our sweet spot, and we have been still serving them. Another project, reverse engineering, where we have been doing it for almost 15 years. High-speed rail interior. Here, the key is when the OEM built those high-speed trains, they had enough volume, so they had used high-pressure die-cast process and able to justify. But now client was looking for replacement of like 10 pieces, 15 pieces. There is no way I can justify the investment of high pressure die casting. So we redesigned reverse engineered to sand cast with a combination of machining and give a cost-effective solution. This is actually for San Francisco trolley. Interesting scoop on that is the mayor really wanted to keep those trolleys working and operational because that's what the visitors think about, taking a ride and in a trolley system. So we worked with the leading company who does all the refurbishment, and we reverse engineered the traction motor housing and both the ends, the commutator end and the pinion gear end, PE end, and end cap castings, and delivered a complete solution to them. So we use traditional method as well as scanning, build the model. When you make the model, you make casting as well as finish machine. So 2 models, and then we go through casting analysis, develop the riser gating, do FEA, so I know which are the critical areas, develop the acceptance criteria, and do the acquisition and get it machined and powder coated and supply. So we have quite a few examples of this. So I think at this point, I would Joe take some questions the audience may have, and how do we handle? Do I give the control back to you?
No, we can leave it here for a
Okay.
second. I would encourage folks to take note of Jiten's contact information that you see on the bottom of the screen there. As you can see, he and his company have worked in a wide variety of processes across the government, across industries, and a tremendous amount of background there. So if you do have questions, please submit them via the chat function that is available on the Zoom taskbar there, and we can facilitate the Q&A going forward here. So Jiten, a couple questions that came up. You talked a lot about casting and a lot about additive, and I know there's a lot of discussion about additive being additive is where I shouldn't say everyone, a lot of people jump to immediately, but what kind of role does casting still play as it relates to manufacturing, and so people don't automatically jump to additive as a solution? Can you talk a little bit about that?
Yeah, I'm glad I normally clarify that. So this is very important. Good question. Additive manufacturing is a big buzzword in the industry all across the globe. And I would say 90% of it, or majority of it, is referred to as what we call metal additive, where you are directly printing metal parts either through laser or directed energy or even binder jet metal particles, almost like powder metal. So the metal additive. What we are referring to for metal casting is strictly a binder jet process where we make the mold, sand mold, out of silica sand or ceramic sand, make core which goes into the mold to make your interior features, again made with the binder jetting, where you have layer by layer and you make the cavity where you pour the metal. The difference, the main distinction is in our approach of additive, we use the same alloy, has the same cooling rate as the conventional sand casting or investment casting, as opposed to metal additive where they have tremendously high cooling rate. So what happens, the properties you get are nowhere close to that the alloy was designed for. So you have to do either a lot of post-processing and there is a lot of issues with the warpage and overall cost, because it takes the envelope size is still limited to maybe 2, 3, 4, 5 cubic foot envelope, whereas our approach and the technology additive of metal casting is our we can do like a Lego style, make a huge mold which we have 20 feet long. You can make it in like a 6 feet segments and glue it together and pour the metal. And once you pour the metal, the whole melting, pouring, solidification, cooling, removal of risers, gates, everything is the same as the conventional. So I know it's a long answer, but additive to us is printed mold, printed core, and printed wax pattern, which is also done predominantly by binder jetting, but also lately we have been seeing FDM method, making it out of PLA. And of course, the oldest technology still continues, SLA or quick cast stereolithography.
So casting is still has a role. Additive is just a tool used in it. In your case.
Right. And we have been using as an industry additive, those FDM, SLA, those processes are around for over 25 plus years.
Mm-hmm.
So we use those to make the patterns, digitally with the additive route as opposed to subtractive by CNC. And so my take on it is right around, late 90s, the high-speed milling came and really took our 8-hour lunches of rapid prototyping processes, because they could deliver quicker, lot more dimensionally accurate without staircasing. So then there was a gap, and then this new wave of additive came with 3D printed mold and core.
Right, and to your point earlier, additive has I hear an echo of myself. Additive has a lot of different applications that people might not immediately think of, and a few things we're working on at Lift, as you probably know, and some folks in the audience may know, cold spray technology, wire arc additive manufacturing. So there's a lot of different things that it's not just printing, plastic parts and pieces that folks may commonly think of.
Correct.
How is the determination made? You talked about some of the reverse engineering and some of that work that you did. The determination about the process that you should take. Is it a combination of process and cost and time, and all of those different things, or just want to get to the best outcome regardless of the time and the cost and the process? Especially when we're talking about, you mentioned the one piece that all you had was a hand drawing from a locomotive from the 50s. I mean, that's you could go any different way, I'd imagine.
Yeah. So cost is the major driver in most of it. But I tell you that my feed water pump for a food grain industry, they were at a point, they gave me pretty much a blank check and say, hey, really, we don't care how much does it cost. I need it in like 2 months' time. Otherwise, I'm screwed and I'll be bleeding 10,000 a day.
Right.
And so in that case, the goal is reliability and the time compression, and you pick and choose the solution. You have a lot more freedom because you are not constrained by a very tight budget. So it's situation by situation.
Speaking of that freedom, we know how important orphan obsolete parts are working with the Department of Defense, because some of these components that they have are from the 50s or from the 40s even.
Correct.
And they don't have the drawings or specs or material requirements. So to your point, you get to have some more freedom there. But are there what kind of thought is there in terms of producing these new parts with more sustainable processes, environmentally friendly processes? Because some of these created back, 50, 60, 70 years ago didn't necessarily have those in mind, I wouldn't think.
Yeah, I mean, so there are two issues. One, obviously, those 50s and 60s or 40s alloys, a lot more improved. So if you have an opportunity to use the modern alloy system and the modern processes, including the heat treatment, you definitely make a much better, stronger, and high-performing component. But what we run into is the roadblock is, some of the the B1, B2, and F-16. They need obviously the flight test or the functional testing,
Right.
and especially the fatigue related, and that's where it becomes a little challenging to find the budget and or more extensive validation they would need. Then only they will put those components into the plane.
Hey, Jiten, you might want to mention that you helped manage that project AFS conducted on E357, which is taking the beryllium out, which is proved to be problematic.
Yeah, no, that's a good point. Actually, lot of that is happening. Politically, if you see the current administration, I think they have put a mandate on the material solutions, which we have a tremendous vulnerability. For example, rare earth. I mean, we know it's in a situation where we don't have any access to, and it's controlled by our so-called adversaries, and government is willing to do tremendous R&D and find such E357 type new alloys or new solutions. There is a lot more work going on in the magnesium and the aluminum non-ferrous alloys, including some super alloys I'm involved, like Haynes 282, which has an excellent elevated temperature creep properties. But these are the material solutions because of the supply chain issue for the sustainment. So I'm glad, Tom, you brought it up. And on that E357, I should mention that we included a bunch of materials into MMPDS, which is the old mill handbook. That used to be our roadblock, because the military engineers, when they design something, that's their Bible. And when we started, like under AFS and under the leadership of Tom Pruka, the person who asked me the question, we had about 60 out of 5,000 plus materials which were cast under MMPDS. And so even if the design engineers, they want to use a peak casting alloy, there is no data available. So we as a society are very progressively working in that area and putting and generating more design allowables, A, B allowables, and including them into the MMPDS, which takes into account the variability, because one of the black eye we get on casting is the knockdown factor, especially the aerospace. Well, if they use the knockdown factor, that kills the casting, because that's a pretty crude ad hoc way of reducing the properties that you get out of casting by knockdown values. So you're using maybe half of, say, 60 KSI. Now the casting is only used for 30 KSI. Well, that doesn't qualify or compete against the wrought products, because they are not using the knockdown. So more scientific approach would be the MMPDS. I know it's a long answer.
No problem.
Hey,
Hey, I
Jim,
encourage
Jim,
everyone
Jim.
to reach out to Jiten directly with any additional questions. Can certainly reach out to us at Lyft. I do want to be cognizant of folks' times and end here on time. So I want to thank Jiten for his presentation today. I want to thank Jiten and PDA for their membership with Lyft. You can saw how much work they've done with us and across the industry and across the network. So thank you very much for that. I do want to thank everyone for joining again today. We do host these a couple of times a month, so please join us when you can. We do have one coming up next week. It's focused on the workforce of the future. We talked about our talent development program. We'll be talking with Square One about the workforce of the future next week, so stay tuned to your emails for that. So thank you so much, everyone, and have a great rest of the day.
Thank you.